So our next speaker is Sam Haynes from the Faculty of Engineering, and he is going to talk to us today about the design and application of a smart battery management system for a small electrical vehicle. Thanks very much, Sam. You can take it away.
Can you see that slide?
Yes.
Yep.
Yes.
Right, cool.
Thanks.
So before I get started, I'd just like to thank Dave, Mark, and Jeff, my supervisors. They've been a big amount of help throughout this research. A drastic reduction in the manufacturing costs of lithium-ion batteries and the global community's response to climate change has led to a surge in electric vehicle sales over the last decade. Bloomberg's electric vehicle outlook for 2021 predicts that by 2040, electric vehicles will have captured 50% of the passenger vehicle market share. And whilst Tesla, Toyota, and other automotive manufacturers have made great strides improving the performance of EVs, the industry still has several challenges to overcome. Range is constantly touted as a barrier to entry for consumers when making the decision to purchase an EV, and therefore battery management systems that allow manufacturers to confidently state vehicle range are an active area of research. The work I've done is centered around the development of a smart battery management system for Lando, as you can see on the right-hand side there, QT Motorsport's latest electric car. Many of the tasks that a battery management system performs rely on an accurate estimation of state of charge. So state of charge refers to the usable capacity that a battery has left. And a perfect example of this is the icon indicating battery life at the top of most phones. In the electric vehicle industry, state of charge is comparable to like the fuel gauge of a combustion car. An accurate estimation of the state of charge gives an indication of range, prevents overcharging and discharging, and it's crucial when analysing and managing the long-term health of the battery. In racing environments such as Formula One, Formula E, and the university level competition Formula SAE, state of charge dictates how hard a car can push before running out of charge, which is a crucial element of strategy. Most existing systems rely on some form of Coulomb counting for state of charge predictions. Coulomb counting tracks how much current has left the battery and subtracts that away from how much capacity the battery had to begin with. This comes with a few problems. It's an open loop system, so there's no correction to errors that are required initially or throughout the discharge process. There's variation in the amount of energy you get out of a battery compared to what you put in if temperature changes. And there's also some nonlinear changes in battery capacity due to discharge rates and capacity loss due to aging of the cells, which you would have experienced with smartphones. To address the issues that are the accuracy issues associated with Coulomb counting, a mathematical process called Kalman filtering is used to combine direct measurement methods with battery models to provide a more robust estimation of state of charge. I'll try not to get bogged down too much in the detail of how Kalman filters works, but I'll give you a short explanation. Kalman filters are a discrete iterative process that produce two estimates of unobservable states. The first estimation propagates the previous best known estimate using a model of the system dynamics. And then the second estimate improves upon the first by directly measuring an output and using Bayesian probability produces a result that's influenced by both the model of the system and the measured output. So this combined estimate is more accurate than if either method was used alone. Whilst there are numerous examples of in the literature of state of charge estimation techniques using Kalman filters and battery models, comprehensive testing of these novel methods in a real-world environment is lacking. So the aim of my research is to test a variety of state of charge estimation methods, firstly with software simulations, secondly with test bench equipment, and finally with a real electric vehicle. This was achieved in 3 stages. Firstly, a custom battery management PCB was designed, assembled, and tested. Secondly, a battery testing rig was designed and constructed that allowed us to cycle a large format battery pack. And lastly, a variety of model-based state of charge estimation algorithms were written to test on the aforementioned hardware. The preceding slides will be categorized into those 3 sections. So the design of the PCB, the design of the battery testing rig, and then the state of charge estimation algorithms. So firstly, the design and building of the custom PCB. Battery management systems typically measure voltage, current, and temperature. And when these measurements are combined with a microcontroller, the system can make intelligent estimations of state of charge and decisions regarding safety critical conditions. The BMS is also responsible for balancing the pack to ensure the cells remain at an even charge level. So this slide indicates the design process for the BMSs that were developed. First, the circuit schematic had to be designed. Then came the painstaking process of finding or building the 3D model of each unique component that was placed on that board. We then arranged the components in the layout stage, sent the board off to China for manufacture, and then finally 14 of these boards were soldered and debugged, which became Lando's battery brains. I could talk for hours about the intricacies of this design, but I'll only mention like one of the features that makes this board unique. I mentioned previously that the BMS boards are responsible for balancing our pack. This involves bleeding off excess energy from the cells with the highest amount of charge to even out the overall charge. This energy is burnt off as heat through resistors, which, if poorly designed, have been known to cause solder to reflow and damage critical components. So the solution we devised was to place these resistors on a separate board that sat atop our BMS. And this allowed for flexibility in resistor values, which determine the amount of heat that's generated from those bleed resistors. And by increasing the distance, we reduce the chance that critical components get damaged. This second slide just shows that we've validated our PCB. So when we took our car to track Queensland Raceway, we managed to capture voltages, currents, and temperatures. In addition to capturing this required data on this track day, it was extremely hot. The track was, I think, 60 degrees. So we also recorded a bunch of our safety critical shutdowns, which was good. So we got an over temperature event, which shut the car down, and an under voltage event, which also shut the car down, which was nice to see. Moving on to the second stage, which is the build of the battery testing system. As an intermediate step between computer simulations and real-time state of charge estimation, a battery testing rig was developed that could discharge and charge the pack at a rate equivalent to real application. So the design featured a 30 kilowatt bidirectional power supply with some auxiliary safety systems. This allowed us to test in a controlled environment. I've included a bunch of diagrams that show the complexities of our safety systems. These were required as the device operates in power ranges that could be fatal if not properly constructed. The main feature of the system is the anti-islanding relay, which was required as the supply can both source current from mains and sink power back into the grid. I probably can't go into too much detail about anti-islanding, but if you're interested, I'd be happy to answer questions after. The image on the left shows the data we've collected during a balance charge, and you can also see me super stoked that everything's working on the right. Finally, we come to our state of charge estimation algorithms. As discussed in my brief explanation of Kalman filters, a battery model is required to make estimations more robust. A variety of battery models were considered, but in the end, a second order RC model was chosen due to its good trade-off between simplicity and accuracy. So on the left there, that's a circuit diagram of the second order RC model that was chosen. And on the right, there's an example of some of the MATLAB script that was written to extract parameters for that model. So with the battery model selected, the Kalman filters were tested. So simple Kalman filters will only produce accurate results when the system is linear, as the filter uses Gaussian distributions in the estimates. Non-linear functions fed into Gaussian distributions will produce non-linear Gaussian results, as we can see in the leftmost figure. If you try and map a Gaussian with a non-linear function, you get a weird, like, skewed Gaussian on the left. The middle graph, as it elegantly demonstrates, non-linear functions can be approximated with Taylor series polynomials. So this gives us derivative information about the non-linear functions around a point, which we can then use to assume linearity around that point. Uncentered Kalman filters work a little bit differently. So they use sigma points, which when transformed through a non-linear function, give us information about how the variance in the mean of the Gaussian will change through that same non-linear function. And then you can rearrange that to get a better estimation of what your Gaussian is once it's been mapped through the non-linear function. These are some of the sort of algorithms that were tested. So we chose 2 extended Kalman filters and 1 uncentered Kalman filter. As this is ideal data obtained from the University of Maryland, we expect the root mean squared error to be quite good, and it was in our case. So a root mean squared error of less than 4% for our algorithms. And then the uncentered Kalman filter was even better than the extended Kalman filters, with errors barely exceeding 2%. In the coming weeks, I hope to test these algorithms in real time with track data gathered from the custom PCBs. And that's it. Thank you.
Thanks very much, Sam. That was really interesting. I'm going to say that I don't have very many intelligent questions to ask, but I'm sure that
you can ask me about
the audience. I do have one question, which is really not intelligent, but I need to know what you named your car after. It wasn't a Mario Kart, was it?
Okay, that's a long story. Do you have the time?
No, short story answer.
Okay, so we had one of our students in QT Motorsports passed away at the end of last year, and his favourite driver was Lando Norris.
Oh.
And so he drives for McLaren, which, as maybe you might know, is an orange and blue kind of car. And so we copied the livery for Lando's McLaren that he drives currently and named the car Lando.
What a tribute. That's amazing. Yeah. Okay, sorry to have asked that question now.
No, that's all
right. Can I please open the floor to any questions from the audience? You just put your hand or unmute if you would like to, but please say your name.
Sorry, Megan Stewart here. Hi, Sam.
Hey.
I have an EV.
Yes.
And when you were showing the first few slides about, you know, the inhibitions the market, you know, people have for buying them, I completely concur. And my dad sold me his one with a dodgy battery, by the way, too. So I think that this would be something amazing if it, you know, if you could. Because I know when my range gets down to about 50, I go, ooh, are they real kilometers or are they not? You know, so this is all the
same with phones.
Yeah, this is all very, very exciting. And you know I'm in applied linguistics, but I think it's amazing what you did. And gosh, when you said painstaking, I could feel it in your voice. That was I don't
want to admit how many months that took to build.
Yeah, great job. Oh, wonderful. Very, very relevant. Thanks.
Thank you.
Any other questions from the audience? I think there's lots of potential for the future here, Sam. Have you got plans for the future?
Yeah, hopefully I'll continue in this space. I've really enjoyed what I've been doing over the last year and a half. So yeah, hopefully I continue.
All right, so talk to your Director of Research Training and your academic leads about a PhD.
I already have.
Excellent work. Thanks, Sam.
Thank you.
We might move on to the next speaker now.